Morning, this is Mr. Smith. We are in section 7.1. As a quick review, (7.1) is about exponential growth functions, and these are in the form y equals b to the x. Okay, so our variable is in the exponent's place. We have this idea of an asymptote. An asymptote is a line that the graph approaches but never reaches. Okay. We talked briefly about how to graph these yesterday. We said we have an XY table approach. We have the graphing calculator piece. And, of course, our knowledge of transformations still applies. So, for instance, here, this -2 creates a vertical shift down 2 units. This x minus 2 gives us our horizontal shift to the right 2 units. And then this 2 up front gives us our stretch factor. Somehow this graph becomes stretched. The domain on all of these functions is all real numbers. I can plug in any x value, and I won't run into any problems. The range is going to generally be from like 0 to infinity. Although if we are doing a transformation vertically, obviously that's going to change the range slightly. Okay, so here, this is an example that we didn't see yesterday, and I'm not going to go through the whole process of graphing it, but I do want to talk about the transformations. So here I get a -3. Again, this is our vertical shift 3 units down. Here I get an x plus 1. So this is going to be our horizontal shift to the right 1 unit. And this 2 is our stretch factor. So again, our knowledge and our understanding of transformations still applies even to this new function type. It'll apply when we start looking at trigonometry at the end of our time together in Algebra 2. One thing to talk about, the domain here is going to be from -infinity to infinity. It says I can plug in any x value. That part will be consistent. But the range, right, so the original function, before I transformed it, would look something like this. But now, let's see if I can excuse me. Now I'm going to shift this down 3 units, and so we should get something that looks more like this, and I'm going to shift it 1 unit to the left. So something like that. And so the domain still, and again, this is just an approximate. This isn't exactly what that graph is, but close enough. To see that the range, if I started at -infinity and I worked my way up on the y-axis, when I get to -3, the graph is not there. But as soon as I take one little step forward, now the graph is there, and so we say the range is from -3 to infinity. Okay? But we don't include -3 because this graph, this line, will never touch the y value of -3. Okay. So, transformations, domain and range, those pieces are still going to be with us for some time to come. All right. But the rest of this time in our section, we are going to work on applying these ideas. Okay, and so this is our biological model, and we'll do a couple word problems here with this. Just one point of clarification. I wrote this was a horizontal shift 1 unit to the right, but we know that horizontal shifts always go the other direction, so this should have been 1 unit to the left, thanks to my astute students who pointed that out to me. All right, so back to our model, just to talk through these values here. All right, so this is pretty much, let's call it a formula, for all intents and purposes. It is a formula where A is our starting value. This is our initial value. R is going to be the percent increase expressed as a decimal. Okay? And T is going to be our time value. Okay? And this creates our formula for exponential growth. Y equals A, initial value, times 1 plus R, so 1 plus this rate, all to the tth power. Okay, where t is our value in time. So let me just come up with an example. Let's say we have 100 rabbits, and they increase at a rate of 20%. 100 rabbits increase at a rate of 20% over the period of 6 years. So the question then is, well, how many rabbits do I have? And so the idea is that after year 1, well, I have 120 rabbits, right? Because 20% of 100, 120. But year 2, they now increase by another 20%, but not 20% of 100, but 20% of 120. Right? So that is the underlying idea of compound growth. And so in this case, the number of rabbits, y equals 100, our starting value, times 1 plus 0.2, all to the 6th power. And of course, we don't have to write this as 1 plus 0.2. We could just write 1.2. This is 100 times 1.2, all to the 6th power. And we're going to rely on our calculators to do this. I don't expect anyone to try to do these problems in your head. Okay. And out of curiosity, I mean, I just totally made up this problem, but does someone have the value for me? Okay, so 298 with some decimals after it. But of course, we don't want to have a part of a rabbit. It gets messy, so we'll just say 298. Is that good? So 1.2 to the 6th power. 1.2 to the 6th power. And then times 100. Yeah, 298. Very good. Okay? So here we go. So this is an actual problem, and we'll go a little bit more in depth here. So buffalo. In the last 12 years, which this part isn't really relevant, an initial population of 38 buffalo, so that's our starting amount, grew by a rate of 7% per year. Okay, so write an exponential growth model given the number n of buffalo after t years. So this is just going to be an abstract. It's going to be an abstract formula. So n equals our starting amount, 38 buffalo, times 1.07, right? 1 plus 0.07, 1.07. And they don't tell me how many years, they just say t years, so all to the 10th power. Okay, so that's kind of part 1 there, right? 38 starting amount times 1 plus 0.07, all to the 10th power. Now, the next statement, though, they say, well, wait, how many are going to be there after 7 years? So this is 38, 1.07, all to the 7th power. Okay, so now I know what the t value is. The t value is 7. So it gives us 1.07 to 7th power. Remember, you need to do the exponent piece first, times 38. And that gives us 61.02. But again, we don't want to have 0.02 buffaloes. So let's just call this 61. Out of curiosity, this is just kind of an aside, what if this had said 61.72? Should I round that up or round that down? All right, so if it's 61.72, I still don't have a 62nd buffalo. All right, so generally we don't want to say that we do. So we'll say that we have 61, and technically that's not rounding then. Right? Because rounding would say you bring it up to 62, so the word that we have for that is truncating. We're truncating this number and ignoring everything else that is after it. We are simply stopping at 61 and truncating it, ignoring all of the decimal values. Just a thought there. Okay, so walking back through this, we have our equation or our formula, n equals the initial amount times 1.07. This was 7%, all to the 10th power. And now they tell us that we're going to have 7 years of growth. And so here we put the t, we replace the t with the 7. we calculate this out at 61. Okay? And now we're going to move on to Part B. All right, so on the next part B, they ask us to graph this model. Okay, so anytime we graph, we're just going to write this as, so for Part B, we'll write this as y equals 38, that's 1.07, and instead of t, we'll use x. Calculators are good on those variables. And then use the graph to estimate the year when there were about 53 buffalo. So should this be the x value, 53 buffalo, or the y value? Should be the y value, right? The y value is the number of buffalo. And so, by the way, what's the plural of buffalo? No idea. You should look that up right now if you're watching the video. All right, so here we go. Y equals, so we come to our calculator, 38, 1.07 to the x power. I don't see the graph anywhere. That's because it's off the screen. I'm also going to graph another equation for our 53 buffalo. Okay, y equals 53. And the reason I'm doing that is because now when I go menu and I change my zoom to fit, you can see here's the level of 53 buffalo, and here you can see where our graph of the buffalo population, the red graph, reaches that point. And so again, menu, if we go analyze graph intersection, we can see at 4.9 years, 4.917 years, we arrive at a rate of 53 buffalo. So, of course, we can round that up to 5. I'm sure they want us to. The other way you could have done this is you could have used the trace option. So there's the trace, graph trace, and now, if we move along here, I see, I have 42 buffalo, 43 buffalo, 44 buffalo, 47 buffalo, 48, 49, and you could just trace all the way up to this point, and you would see that it would take you about 5 years to get 53 buffalo. Okay, so graph the model, use the graph to estimate the year when there were about 53 buffaloes. So in year number 5 of our situation, of our experiment, we would get 53 buffaloes. Okay? So the next application is in finance. And what you'll see here is that this equation, this formula, is actually identical. It's identical to the one we just saw, except that we take into account n here, where we're going to compound your money or your investment n times a year. Now, most savings accounts might compound your interest monthly or quarterly, depending. I've seen a few types of investments that will compound interest daily. And so to accommodate that, we have P. This is our initial amount, but in finance we call that a principal. That's the initial amount. We get 1 plus the rate, but here we also divide the rate by the number of periods we're compounding by. And then we take that all to the n times t power, okay, where t is still time, and n again is the number of periods that we're compounded by. So if your savings account compounds quarterly, then you're going to divide the rate of interest by 4, and then multiply the number of years you're investing by also 4. Okay, but this formula is very, very useful and also needs to be memorized. Okay. And so here is a standard problem in finance. We have $4,000 in an account, and it pays 2.92%. I wish I could find a savings account that paid 2.92%. Mine, presently in the year 2013, pays 0.75%, and that's a very good rate. If you go to Chase right now, it'll pay you like 0.01% on their savings account, so pretty pathetic. Anyways, here we go. So I have 3 different compounding periods: quarterly, daily, or yearly. Quarterly, daily, or yearly. And so to calculate these, we start with our principal, $4,000, 1 plus the rate, which is 0.0292, 0.0292. And since we're doing it quarterly, we're going to divide this by 4. And then we'll take this all to the 4 times the number of years. So our number of years is 5 years. So 4 times 5 power. and this will give us how much money our investment will have made if we made 2.92% compounded quarterly for 5 years. Okay. For part B, if we're doing this daily, it'll be almost the same calculation. It's just instead of dividing by 4, like we did previously, we're going to divide by 365, assuming it's a standard year. And then we'll take 365 times the number of years of our investment, which in this case is 5. Okay. If we do this yearly, this is y equals 4,000, 1 plus 0.0292. In this case, we'll only have to divide it by 1, so we really don't even need to put that. And now, of course, we're investing it to the 1 times 5 years power. Okay. So if you're watching this at home or in the class, I'm going to ask some of you to calculate each one of these 3 values so we can take a look at them. Okay. So if you're watching at home, pause the video now and work through these 3 calculations. All right, so after we've done all 3 calculations, we can see that if we only compounded this money 1 time a year for 5 years, we end up with $4,619. If we compounded it quarterly, we make $7 more, not really substantial. And lastly, if we compound it daily, we make $2 more. Again, not really substantial. I think mostly these compounding periods are more a sales gimmick or a convenience rather than an actual difference in value, unless you have a lot of money, right? So $4,000, it doesn't make a big difference. $400 million, now the compounding periods will make more of a difference. Okay. All right, so here's one last problem. If you're watching at home or in the class, you can work on this one, and in a moment I will have the answer up. Okay? Great. Otherwise, this finishes the video. Thanks for your attention. Have a good day.